Hello, Theodora. Hello.
Hi, everyone.
Uh, the session just
Would you
end.
like me to share my screen?
Oh, yeah. But can you wait for 2 more minutes because the session just before just ended right now, so people are still entering the
Mm-hmm.
room.
Oh, yeah, yeah, yeah. Of course, of course.
You can start sharing your screen now, so we can be prepared.
Okay.
The survey talk session will start shortly, so please come inside. Okay, so let's begin with the survey talk session. And I'm the session chair, it's Jiwon Kim of Seogang University. Thank you for joining us to this session. So in this session, we have two presentations. So the first speaker is Professor Chaspari. So are you ready for the presentation?
Yes.
Okay, yeah. So the title is Emotion and Affective Speech Processing and Technology. Would you please start the presentation?
Yes. Thank you so much.
Thank you.
Hi, everyone. Good afternoon. My name is Theodora Chaspari, and I'm an assistant professor in computer science at Texas A&M University. I hope that everybody can see my screen. So today we will talk about affective speech technologies, and we are going to discuss fundamental concepts in affective speech processing, as well as early work on affective speech representation. And then we're going to move on to more recent studies on deep learning for affective applications and emerging topics. So affective technologies enable computers to identify, process, and simulate human emotions. And they lie at the intersection of computer science, signal and speech processing, psychological science, and cognitive science. And the human affect may vary in several ways, including its duration, intensity, and specificity. And affect can play an important role for regulating human cognition, psychology, and social interactions. Human affect is inherently multimodal, since it can be expressed by various channels, such as our facial expressions, our body gestures, and speech. And for the purposes of this presentation, we're going to mostly focus on affective speech technologies, which can process and characterize speech signals to identify the emotions that are embedded in them. So why is speech an effective measure of affect? Different types of emotions are characterized by unique configuration of acoustic cues, as it has now been established by various studies. And especially speech patterns of prosody, and by prosody we mean pitch and amplitude modulation and segmental duration, can carry affective information. Therefore, it has become apparent over the last years that we can quantify speech affect and one's affect by encoding certain characteristics in their speech signals. And taking a step back into the history of affective speech technologies, I'm going to quote a sentence from Klaus Scherer from his well-cited 2003 speech communication publication. And what he said was, at that point in 2003, in recent years, speech scientists and engineers who had tended to disregard pragmatic and paralinguistic aspects of speech have now started to devote more attention to speaker attributes and emotions, often in the interest to increase acceptability of speech technology for human users. And while the engineers working in this area showed a little interest in emotional speech until fairly recently, this situation has drastically changed, as demonstrated by the INTERSPEECH conference in Newcastle. And what this refers to is a workshop that was organized as part of the 2000 INTERSPEECH, where if you actually go back to the proceedings of this workshop, you will see very well-known speakers in the field that had participated at that time. And topics of the workshop, among others, included emotion theory and paradigms, description of emotion in speech, as well as automatic recognition and synthesis for emotion. So fast forward 20 years later, With the advent of AI, artificial intelligence, and Internet of Things technologies, affective speech processing has seen a tremendous progress. And researchers and practitioners study affective speech technologies for various domains. For example, these technologies can be used in healthcare, where tracking affect can be quite useful for understanding degradations of mental health outcomes. Also in education, obtaining information about a learner's affect can be quite valuable in understanding the learning processes and potentially designing intelligent assistive technologies for improving learning outcomes. And overall, tracking emotions in a team can contribute to promoting functioning, mitigating conflicts between team members. Affective speech technologies are also becoming more and more ubiquitous with the advent of IoT devices and such as home assistant devices, smartphones, and smartwatches, and therefore can have a tangible impact in people's lives. The tech industry is also becoming more and more interested in investing in such technologies. Here you can just see some examples of the companies nowadays we enable speech processing applications for emotions, and the surveys predict that this interest will increase over the next years. For example, by 2022, which is actually now, 10% of personal devices will have cloud-based or on-device-based emotion AI capabilities, and the global emotion analytics market is predicted to increase to 140 billion by 2025. However, despite the promising outlook, there are several technical, computational, and ethical challenges that are related with affective speech technologies. First of all, there is an inherent uncertainty in the measurement of human affect. Human affect, by definition, is an underlying state, and what we can actually capture by speech is whatever is expressed, which is a noisy version of this underlying state. Speech expressions are quite heterogeneous and complex, and also confounded by the inherently high interindividual variability, as well as other conditions and confounding, such as the interactions people are involved in and their daily activities and events. Also, labels pertaining to affect can be also subjective and limited in number, and many times difficult to obtain. And finally, as with any AI-based technology nowadays, public opinion tends to be skeptical about using and deploying such technologies. So throughout this talk, we're going to discuss signal processing and machine learning methods that have been employed to address some of these challenges. And of course, some of these challenges are also very much ongoing. And before diving deeper into this presentation, we will discuss a few fundamental concepts. So as you can see here, affect is a broad range of feelings that people can experience, and it embodies both moods and emotions. So emotions are intense feelings that are usually short-term and typically are directed as part of a stimuli, as part of a tangible stimuli, while on the opposite, mood is a state of mind that tends to be less intense than emotion, but is longer, so spans from minutes to hours to days, and might not always be stimulus. So in speech processing community and affective computing community, emotion has been usually represented by what we call discrete and continuous representation. And a discrete representation refers to categorical emotions such as anger, happiness, sadness, while continuous representations usually refers to a 2- or 3-dimensional representation of emotion into valence, arousal, and dominance. Mood, however, is typically characterized in the context of clinical applications via several clinical scales, and examples of mood representation that we have seen in prior work include symptomatic mood, such as depressed, manic, or asymptomatic mood. So, of course, as with any intelligent intelligent tasks. Affective speech processing requires data, and the affective speech processing community in the past 20 years has put a lot of effort and interest in generating data sets that can be useful for the task at hand. So data sets can be categorized as important, can be categorized, the emotion elicitation methods. So we have what we call active data sets, which were predominantly in the beginning of the community. And in active data sets, usually we had either people or actors act specific emotions, while these data sets can be quite clean and actually include emotions with a balanced distribution. However, these data sets tend to be quite unnatural. On the opposite side, we also have what we call evoked emotion elicitation methods. And as part of these methods, speakers are asked to are part of a context, and emotions are also quite artificially invoked by the speakers. And finally, we have what we call natural or real emotion elicitation methods, in which we usually monitor and observe emotions in the wild. And of course, these data sets, this type of elicitation methods can be quite important because it elicits natural emotions. But on the other side, this is usually a data set that is more hard to handle because it has inherently more noise, imbalanced data sets, and a lot of uncertainty. And here you can see from a paper review some of the commonly used data sets that have been used for emotion recognition. And examples include the Berlin Emotional Dataset, Recola Speech Dataset, Interface, IMOCAP, and many others. So once we have collected data, another important part is labels. And usually when we are talking about active emotions, that's quite straightforward because labels are predefined. However, when we're talking about natural emotion elicitation methods, we have a few ways to obtain labels. So one way is to obtain people's self-reported emotion. So essentially, we are asking people to annotate how they perceive their emotion at some point. And provides one's perspective about their emotion. It is quite useful. It is widely adopted. However, there is the challenge of subjectivity that goes into self-reports, as well as recall bias. In order to mitigate recall bias, recent methods, especially our methods on longitudinal data processing, have started using ecological momentary assessment, which essentially provides, administers self-reports while people are in the process of doing some task. On the other side, we also have third-party labels that can be obtained either via crowdsourcing or by having human experts observe the data and provide their own perspective about the target's emotion. And this type of labeling is usually focused on what is observable. So of course, there is an inherent noise that goes into this type of labeling. And of course, we have several other challenges that are involved there, such as the time alignment between annotators and the temporal segmentation of the data. So the affective speech processing community has put in a lot of work in characterizing the subjectivity of emotion perception when that comes from the labeling. So a lot of work has been performed on modeling inter-annotator agreement. And here you can see some work that has been doing how inter-annotator can actually help obtain better labels. Here you can see, for example, an emotion labeling method in which the same annotator has labeled activation in a continuous scale twice. Also, there has been some work on modeling annotator-specific distortions, such as distortions that are related to the reaction lag of the annotators, temporal shifts, and here is another type of work where essentially the final for a speech signal is being formulated as the result of several other annotations that have gone through a filtering process. And as part of this graphical model representation, what the authors have done is that they have attempted to jointly model both the characteristics of the filters for each annotator, as well as the final annotation result. There has been also a good amount of work on how we can temporarily align labels from the annotators, for example, using dynamical type warping transformations, as well as more advanced methods of these transformations. And recently, there has been also some work on modeling the relative change in the emotion rather than the absolute patterns. Now, within the labels, we have to somehow represent speech so that we can mathematically express that, and then using machine learning and AI techniques, we can actually find patterns from these representations. So early work had predominantly focused on knowledge-driven representations, and many of these representations are designed based on psychoacoustic properties that attempt to characterize fine-grained patterns of affect in speech. Examples of these representations include descriptors of prosody, vocal excitation, and vocal tract, and spectral descriptors. And here you can see a schematic representation of how this used to work. So essentially, once we have a speech signal, we segment the speech signal into shorter term windows of 20-30 milliseconds. We have low-level descriptors that describe the prosody and other spectrotemporal characteristics. And usually these low-level descriptors used to be summarized into a high-level descriptor that used to come from the statistics, from the statistical of the low-level descriptors or other functionals. The community has put in a lot of work in characterizing speech signals in using similar knowledge-driven representations. Examples of this work are derived from the INTERSPEECH computational paralinguistic challenges, as well as from other toolboxes such as Pratt, OpenSmile, and many others. However, the challenging in interpreting these types of features is that eventually we can get a very large number of acoustic descriptors. So in 2015, and at that point, actually the community had matured in knowledge-driven representations. There was an interdisciplinary meeting of voice and speech scientists in Geneva, and they came up with what we call now the Geneva minimalistic acoustic parameter set, which is a selection of voice parameters with theoretical significance and also with good performance in recognizing emotion in speech. So this reduced set of parameters includes frequency-related measures of speech, energy and amplitude-related measures, as well as spectral balance measures. So beyond now these knowledge-driven representations, with the continued advancements in deep representation algorithms, we also have data-driven representations of affect in speech. And here is one of the first studies that has attempted to learn affective representations from the speech spectrogram. And essentially here what we see is a version of a convolutional neural network that has been learned in order to derive emotional spectrotemporal patterns, and then it has eventually learned to output an emotional label for speech. This neural network had been also pre-trained using a sparse autoencoder in order to better accommodate for the sparsity of the data in speech, and it had shown promising results across various speakers as well as across various noise levels. Now, beyond that, there has also been other studies that attempt end-to-end learning from raw speech has been proposed. And here is one of the first studies that attempted to learn emotional representations from the raw speech signal using convolutions and max pooling operations, followed by temporal representations of speech using by LSTMs. And this study actually had found that the activation of LSTM cells was associated with prosodic features. So beyond that, of course, there have been multiple studies that try to derive deep affective representations. And you can also see another study that has integrated multi-temporal dependencies between speech frames. And using this integration, the authors were able to show similar performance between these features and hand-engineered features in IMOCA and MSP Improve. So while deep learning representations are quite promising for affective speech processing, we still need to combat data scarcity that comes with that. So there have been studies that have proposed the synthetic generation of emotion speech data. One of these studies has the generative adversarial network to mitigate the uneven emotion class distribution, and has obtained promising results in real life data that contains speech from TV shows and podcasts, yielding a 5 to 10% relative improvement in emotion recognition accuracy. In another study, an adversarial autoencoder was used for the same purpose. And the purpose of the adversarial autoencoder here was that the latent vector of the autoencoder was regularized using this type of adversarial learning. Promising results were obtained here in that the authors found that when they combined synthetic data points with real data points, they got significant improvements for speech emotion recognition. With the advent of speech technologies in the wild, it has become also more and more important to learn generalized representations that correspond to novel situations that have not been observed in the data that we have in hand. So a prior work in affective speech processing has also focused on how we can handle domain mismatch, which can be a result of different types of labeling, different speaker traits, and interaction characteristics. As part of preliminary studies in this domain, prior work has used, of course, feature normalization and supervised domain adaptation, such as adaptive and incremental support vector machines. Here you can see some work that has been done using adversarial learning. And as part of this work, the authors attempted to minimize mismatch between domains via training a domain classifier apart from an emotion classifier. Well, the domain classifier was to generalizable emotion representations, so that eventually the different domains from which speech signals corresponded to were not differentiable enough. And the authors obtained actually promising results in this type of fully unsupervised domain adaptation. These are emotion recognition accuracies using the target task, the target data, and the authors obtained improvements, significant improvements when using this proposed adversarial learning, as compared to just using the source data for training the emotion recognition system. After that point, there has been also more work that has attempted to leverage information between relevant tasks in an effort to learn generalizable emotion representations in speech. Prior work has used multitask learning, progressive neural networks with various auxiliary tasks, such as domain recognition, gender recognition, and speaker recognition. And here you can see some of these architectures that were designed for this purpose. There has been also recent work as part of our lab as well on modeling relative distance between classes rather than absolute patterns, and how these metric learning approaches can help in diffuse learning and to transfer knowledge in generalizable manner in spontaneous speech datasets. So finally, there has been also quite some effort recently in pre-training speech emotion embeddings using a large-scale data. So eventually this would lead to having this pre-trained embedding that could be architecture for that, which is called EMONET, is assembled from 20 speech emotion recognition corpora. It uses a deep ResNet with residual adapters, and it has provided improved performance in 21 out of 26 corpora in which this has been trained. Now, transitioning again towards affective speech technologies in the wild, we also acknowledge the fact that in the wild, we have a lot of confounding factors that come into play when modeling human affect. And beyond background noise and recording conditions, there is also contextual dependence of emotion. So prior work has attempted to model temporal dependence of emotional information in the long term, as well as a dependence of emotion on personal interaction, and has actually obtained significant improvement in performance improvements when modeling emotion not only of the current speaker but of other speakers in which the target one is interacting with. When we look at speech in the wild, we have also found benefits for incorporating contextual factors such as stress, fatigue, intoxication, physical activity, because all of these factors can affect emotional speech production. And also, in addition to that, a lot of effort in the community has also gone in personalizing emotion models. So prior work has acknowledged the fact that there is a large interindividual variability in emotion and affect production, that speech characteristics, speaker characteristics. So prior work has attempted to propose person-specific models that make decisions separately for a different participant, but also group-specific models that somehow group participants either on a knowledge-driven manner or in a data-driven manner and result in more reliable models this way. These are some examples of mechanisms in which personalization was achieved. So early work has attempted to use person-specific feature normalization and decision thresholds, but there has been also more work that has used domain adaptation, where in this case, each specific speaker is a different domain, as well as work that has used multitask learning to leverage joint information across individuals. And now, when it comes to personalization, which is essentially our effort to get as much information from a certain speaker as we can, we understand that this might not always go hand in hand with privacy preservation. And privacy preservation has been identified one of the main challenges in AI technologies, as recently as this April, that restoring personal privacy was also identified one of the main challenges by the ACM. So there has been some prior work in affective speech technologies on how emotion recognition systems can actually leak one's identity and one's demographic information. So in this study, for example, the authors have found that leveraging speaker verification embeddings can help in retrieving emotional content. And in another study, the authors have attempted to quantify the demographic leakage from acoustic and linguistic emotion embeddings. And you can see here various numbers and the comparison between the leakage between acoustic and linguistic embeddings. Now, there has also been some effort on preserving privacy on the learned emotion recognition embeddings. And this effort has attempted to index noise that is being learned via adversarial learning, as well as to conduct a multi-source domain adaptation so that speaker invariant characteristics can be learned. And also, now that we are moving more into this cloud-based IoT framework, previous work has also looked at federated learning mechanisms for privacy preservation and emotion recognition. In a different view, our work has also tried to examine some of these concepts, and we have tried to see how we can generate anonymized speech that preserves some type of affect information. And for that, we have used an autoencoder framework that has been trained with a competitive loss between removing as much of the speaker information as we can, but retaining as much of the affect information as possible. Moving more into ongoing challenges and emerging research topics, there has been a lot of interest from the AI community about how affective technologies can become more fair. And also this is motivated by recent findings from automatic speech recognition technologies that have been observed to mitigate and propagate existing demographic bias, either through the data or through the way some of these algorithms were being trained. So in the same token, affective speech technologies are starting to investigate sociodemographic bias across all stages of data acquisition, analysis, and interpretation and human AI interaction. We have seen as part of our studies a significant difference at the intersection of race and gender with respect to commonly used prosodic features that are used for emotion recognition. And also, there have been various interesting studies on how on quantifying fairness in affective technologies. So there has been studies that have quantified statistical parity. What we mean is the difference between positive rates between sensitive and non-sensitive groups, and they have compared these types of measures between language characteristics, audio characteristics, and visual characteristics. And similarly, this is another study in which the authors observed differences in performance when it comes to some type of affect recognition between verbal, paraverbal, and visual measures. So a few more thoughts on how we can actually try to be more inclusive when we use technologies. Affect bias is very important when it comes to speech. Other types of biases that can occur are across cultures and across languages, also across neurotypical and atypical individuals, as well as groups that have not been traditionally considered, such as LGBTQ+ groups. As part of the last discussion topic here, moving more into explainable deep affect representations and thinking more about human AI interaction, there has been some prior work on how we can visualize learned representations of affect into better understand the inner mechanisms of a network. As well, incorporate knowledge from speech production into deep learning, into producing more explainable deep learning models for affect recognition. And when it comes to affective speech technologies, beyond the actual design of the system, it's also important to consider several HCI perspectives when we do that. And borrowing here from a Kai paper, several perspectives to be mindful of are how we can highlight saliency in our data, how can we describe some samples in a logical manner that makes sense to the user, and how this description can be actually adapted to a specific user, and how we can use counterfactual thinking that actually highlights relative differences and relative comparison between samples that are more intuitive to a human user. So I take on these technologies, and that by no means is fully comprehensive here, but 20 years later, after this industry community has come actually a long way. We have empirical findings in terms of knowledge-driven and data-driven representations that are quite novel and have powered technologies in the real world. It's important for affective speech technologies researchers to keep incorporating domain expertise from psychological and cognitive sciences. It is important, and many groups have started now thinking and actually implementing and validating affective speech technologies in the real life. And also the community is thinking more and more about how we can design affective speech technologies for all people, independently of their demographic characteristics or background. Or fine-tuned to people's background. Public trust is, of course, a problem and a challenge that has to be addressed. How can we increase and properly calibrate users' trust on affective speech technologies is an important dimension. And finally, since affective speech technologies are so core into the human knowledge, it's also very important to think how we can design and adapt and apply these technologies in an ethical manner. And affective speech processing, of course, should be at the forefront. Look in ways that we can minimize harms and maximize benefits from these technologies, and make sure that we engage in conversations with public industry, with policymakers, on what these technologies can achieve and how these technologies can be more effectively incorporated and integrated in humans' lives. And with that, I would like to thank you. And if there is time for any questions, I would be happy to take any questions. Thank you very much.
Yeah, thank you very much. Any questions or any comments? Oh, yes, please. And please go to the microphone, because this presentation is broadcasted in real time.
Thank you for the nice presentation. In paralinguistic space, they usually, for speech, they divide it as per the duration, they divide it into 3 traits: short trait, medium trait, long trait. And mood, which was in your initial slides, are considered in the medium traits as the duration. Long traits are depression, and emotions are the short traits. Right? So are there any databases or work that have been done to capture the medium traits like moods? Because there's a lot of work on emotions, but and now I see a lot of work in depression, long traits, but are there something that has been done on moods, the medium traits?
Yeah, that's a great question, and I think this topic is a little bit is relatively less explored. I know that there has been work that comes out from several researchers on that front, and how this mid-level representation could be actually modeled. And I think recently there are some data sets that have started. Again, the problem with some of these data sets are privacy and confidentiality issues because of the clinical outcomes that are related with mood. But there is definitely, I think, the community is moving towards that direction more and more.
Thank you.
Thank you.
Hello, thanks for your talk. I have a question about what we call it non-native emotions. We have to communicate more and more in the international settings, like here at the INTERSPEECH. We have to speak English, and a lot of people, it's not their non-native, not their native language. And like you said, in your inclusiveness, languages and cultures, people have different ways of expressing emotions. So how do they transform transfer their native emotions to non-native speech. Has this been studied?
I'm sure there is some work out there. On the top of my head now, I cannot think of anything. But of course, there is the since speech is very much affected by whether a speaker is native or non-native, I could potentially think that this factor would affect the corresponding speech representations that are learned or are being designed as part of these systems. I would completely see how native and non-native speakers would express emotions in a different way, let's say in an English language. But beyond that, it's quite important to also recognize the fact that speech technologies and affective speech technologies have been predominant languages, and it's I think bringing this awareness more and more into this community about how can we include languages from Asia, from Africa that have dialects that include a variety of dialects is quite important, and we have to actually to be more and more aware and recognize some of these issues.
Okay, thank you very much.
Any other questions? Okay, thank you very much again, Ilse, for your presentation. Thank you.
Thank you.
So